So we've discussed what the magnetic field of a current loop looks like, but a current loop is actually going to be incredibly important. So it isn't just what the magnetic field looks like, but how we can actually use this and interpret this. So first to note is that there's two distinct sides. There's the side that the magnetic field is entering, and then there's the side that the magnetic field is leaving. And we find that this actually orients with the Earth's magnetic field. Where the magnetic field leaves always points towards north. Interesting. And in general, this is actually going to behave like a small permanent magnet. So when you think of a normal little magnet that orients itself with the magnetic field and picks up little metal things and has two sides that repel and attract depending on whether they're the same or different, this little current loop does all of the exact same things. We call this an electromagnet, simply meaning that we've used electricity, in this case current, so that's the electro part, to create our magnetic field. And again, in this case, the magnetic field is behaving just like a permanent magnet. So this is an important distinction. We've talked about the magnetic field from wires, and in that case you get a magnetic field, but it doesn't behave like a tiny little permanent magnet. A very long wire has magnetic fields around it, but it doesn't have a south side and a north side. This one does. So that's the distinction here. There are a lot of different wire shapes that will create magnetic fields, but this one actually has a south and a north pole, or at least a side we can call south and a side we can call north. We can literally test the interactions with a little permanent magnet in order to figure out which side is north and which side is south. So if we have the magnetic field pointing towards the north side, we have a repulsive force. Now, we know that north and north repel, so we would say that the side the magnetic field is facing away from is north, and here, when it's facing towards the magnet, that would be south. Now, on the other hand, if we keep this oriented the same way, we still have north on the right, south on the left, and now we see that it attracts the permanent magnet. So again, we see that this behaves just like a permanent magnet, and that includes attracting and repelling permanent magnets. What you might imagine is we can actually then create two little dipoles, and in this case, if they both have fields pointing to the right, do you think that they're going to attract or repel? So go ahead and take a moment to think about that. And note that both of these have current going in the same way in order for them to have the same alignment. Now, again, north is going to be the side where our magnetic field leaves. So we actually end up here with north on the left one, south on the right one, facing each other. That means the forces you're going to get are actually attractive forces. So this is just something to think through. We get to define north and south, and based on this we can think of the way that two current loops are going to interact, or that this current loop is going to interact with a permanent magnet. So note that we said that north was the side where your magnetic field is leaving, and south is the side where your magnetic field is entering. So what's amazing about this is not only do we have south and north poles, but the magnetic field of a current loop looks just like the magnetic field of a permanent magnet. So note that for your permanent magnet, the north side is where your field is leaving, and your south side is where your field is entering. So in this case, this is a fairly flat permanent magnet, right? Note how it's oriented. So this would be a very thin disk, for instance, not a long bar magnet. And the orientation here does matter a little bit. So that's one thing to note, that we can create this magnetic field from a simple ring of current. And as I mentioned before, if you just take literally a ring off your finger and try to put current through it, it's not really going to work. You have to actually have a wire coming in and a wire coming out to keep that continual flow going. But as we said before, if you have a shape that looks kind of like this, and a loop, and then a wire out, that works pretty well as an ideal loop. So we can't make this perfectly in the lab, but we can come pretty close, and this simplifies back down to that. So what we're talking about here is magnetic dipoles. What does that mean to have a magnetic dipole? Where, well, di equals 2, and we have two sides, north and south. And again, if you think back to other shapes, such as one really long straight wire, you don't clearly have one side where the field is leaving and one side where the field is entering. So that's why this is specifically called a dipole, since we can clearly find that side where they're entering and the side where they're leaving. So that's all a dipole means. We have this out and we have this in. Another way to think about it is we have kind of these two fundamental things next to each other. So what we're going to talk about next is the magnetic dipole moment, and you'll start to remember, hopefully, how this relates to the electric dipole. So remember that we met the electric dipole a few chapters ago that had a positive and negative charge very close to one another. And here, again, we have a south and a north very close together, so there's a similarity, but we never have a chunk of magnet that is only south or only north.